Okay, we're now looking at transformations of exponential graphs. On your information sheet, you have this representation of an exponential function, and this is the graph that goes along with it. So we've already seen we have the basic exponential function y equals b to the power of x. If we have a multiplier at the front, this a, that is our dilation factor in the direction of the y-axis, so that will stretch out the graph in the vertical direction. So it either stretches it out, makes it kind of stretch it that way, or so taking it further away from the x-axis, or it will bring it closer to the x-axis. Okay, so then we have k on the end here, which is referring to the vertical translation, similar to other functions you've seen. Okay, so if we've got a positive value for k, then it's going to shift it up. Negative value for k is going to shift it down. And the effect that it has here is it's then going to change the value of this the y-intercept. It's also going to change the value here when your x value is equal to 1. And the dotted line that you see here is the horizontal asymptote, which for our basic exponential function is, as we saw, the x-axis. But for a translated graph, it's this value y equals k. So that's the equation of our asymptote. The asymptote is only changed as our vertical translation changes. Now, it says here that we're not concerned in this course with horizontal translations. That is not exactly true. It possibly means that we could have a horizontal translation. What we would notice then is that we would have y equals b to the power of x, minus or plus some value h in the power. Okay, the plus k on the end here is a vertical translation, but if we've got our x plus or minus some number here in the power, then that's going to shift our graph left or right. If it's minus 5, say, it's going to shift it to the right 5 units. If it's plus 5, it's going to shift it to the left 5 units, just like we've seen with other functions. Okay, so keep that in mind. All right, so over the page here, let's have a look at a few of these examples here where we're just looking at finding the y-intercept. Just like with any function, when we're wanting to find the y-intercept, we let our x value equal to 0. We've already seen that if we have a basic function, y equals, say, 5 to the power of x, then the y-intercept is going to be at 0, 1, because when x is equal to 0, y is equal to 5 to the power of 0, which is 1. But here we see we've got some transformations occurring. Here we've just got a dilation factor of 2, and so the y-intercept will be 2 times 5 to the power of 0, or 2 times 1, which is 2. For this function here, then we have y equals 3 times 2 to the power of x. Notice the difference here. You can either have it written as 2 with the multiplication symbol, 2 times 5 to the x, or you can have brackets. They mean the same thing, 3 times 2 to the power of x. So in terms of your y-intercept, when x is equal to 0, then we've got 3 times 2 to the power of 0, which is 3 times 1, which is 3, plus 1 on the end, giving us y equals 4. And so our y-intercept here is at 0, 4. And then another example, this is y equals 10 times 3 to the x minus 4. So if x is equal to 0, then as in with all of them, whatever your base is, the 3 to the power of 0, or 2 to the power of 0, or 5 to the power of 0 is always going to be 1. But here we've got 10 times the 1, which is 10 minus 4, which gives us 6. And so our y-intercept is at 0, 6. Okay, so that's an important part of graphing exponential functions, is determining your y-intercept. we saw that the value A out the front is our dilation factor. Of course, if A is negative, okay, A is less than 0, then the graph will be reflected in the x-axis. Okay, so here we've got two functions essentially the same, but one is positive 4 out the front, this one is minus 4 out the front. The shape will be exactly the same, except this one is simply reflected in the x-axis. So your x-axis acts as your mirror line, and this blue curve is reflected over and becomes the red curve, as we've seen with other functions as well. Okay, so that's all important to keep in mind. Notice that reflection is not changing the asymptote. The only thing that changes the asymptote is the the vertical translation, that value of k on the end. All right, let's just have a look at this example here as the only example we've got just for sketching the graph. And this is basically what you need to do for all of exponential functions. We want to label the asymptote. Okay, so we put the asymptote in as a dotted horizontal line. We want any axis intercepts, so there may or may not be an x-intercept, depending on what the transformations are that have occurred. And we want to put one other point on the graph. Okay, so let's have a look here. The first thing here, finding your y-intercept by letting x equal to 0. And so 2 to the power of 0 is 1 plus the 3 on the end, which gives us 4. So we have the y-intercept of 0, 4. Asymptote. Remember, we saw previously that our asymptote will have the equation y equals k, based on this being your equation for the function of an exponential function, right? So a times b to the x plus k. If we have a number here on the end, then that corresponds directly to our asymptote. So in this case, it's plus 3. So y equals 3 is your horizontal asymptote. And so we draw a horizontal line, as we can see here on the graph, horizontal line through the y value of 3, and just having written here y equals 3 as the equation of that line. We've got here our y-intercept of 4, and this as our one other point. You could take any point you like. I've just chosen x equal 1 because it's pretty easy to use. When x is equal to 1, y will equal 2 to the power of 1, which is 2 plus 3 is equal to 5. And so we here have this point 1, 5 plotted on the graph. And so that's all we need in this case. You can see there's no x-intercept because it's not reflected and it's translated up. If it had been translated down, say it was y equals 2 to the x minus 3, then it would have been not reflected, but it would have been translated down, and so it would have crossed the x-axis, and so you would have had an asymptote down the bottom here. Say if it was y equals 2 to the x minus 3, then it would have crossed down, probably looked something like that, same shape, but it would have had an x-intercept here, and a different y-intercept, of course, and the other point would have been different, but our horizontal asymptote would have been y equals negative 3, and it would have been graphed like that. And so in that case, we would have needed both the y and x-intercepts. So you need to just look and to determine if you need an x-intercept or not. Sometimes you will, sometimes you won't. Okay. So that's really it. I suppose that's the only other thing here is to state the range. Remember, the range, of course, is your set of y values that is on your graph. So I'm just going to get rid of this here. Okay. And so our range is our y values belonging to the set of values. Now, what is our smallest y value? Well, it goes down here to y equals 3. We know it doesn't actually reach that value, and so we use curved parentheses here and put 3 there to show that it goes up to but not including 3. That's our lowest, our minimum. Remember, we always put our minimum value first, then our maximum value. Well, there is no max, it just goes up infinitely, and so we would show that by using the infinity symbol, and so that is our range for this function. Okay, so what I want you to do then is to notice down here, the work we'll look at is exercise 4D. Now it's not all of it really, it's just question 5. So if we have a look, this is the exercise that you have here on question 5, all of these. Alright, so don't worry about this one here, E, okay, because that's not really important. So don't worry about E, but you can graph all of these others. Okay, sketch the graphs, give the equation of the asymptotes, the y-axis intercepts. If there is an x-intercept, put that in as well, even though it says they don't. It is important that you do. Okay, so put your x-intercepts in there as well, and put one other point on the graph. So follow what I put in the example, please. All right, so that's about it. I mean, you don't really need to do these others because they're kind of graphing ones that you won't need to do in this course. So that's why we're just really looking at question 5 here. If you finish that, you may well have some other stuff to finish off from previous exercises. Please go on with that. And then on Monday, we're going to get stuck into doing the next thing, which is graphs of log functions. If you want to read ahead, please do. That would be good. But otherwise, we'll look at it on Monday. Thank you very much.